sprinkler technology is being pushed to its limits. Modern material handling equipment is driving storages within warehouses higher and higher. And there's recently a trend to going into automatic storage and retrieval systems, which are pushing storage heights as high as 37 meters. And in the forest products industry, there's a transition from using clamp trucks to overhead cranes, which is doing two things. It's driving storage heights from about 12 meters up to 30 meters, and it's automatically making these arrays open arrays instead of standard or closed arrays, making them more intense in fire propagation and more challenging to protect. Even at FM Global, our fire testing is limited to ceiling heights of 18 meters. So how do we drive protection for our clients that have these higher ceiling heights and for conditions that we cannot test within our laboratory? Today, I'm going to talk to you about the future of sprinkler technology. And I'm going to do that in two aspects. First is how we're going to develop protection solutions going forward. And then we're also going to talk about new protection solutions for situations where traditional sprinklers are no longer viable. So for years, the only way to get protection point was through large-scale testing. You would set up a test, you would conduct the fire test, and you get a result. And then you would change a variable. And then you get a single discrete point, pass or fail. If you wanted a different protection point, you'd have to change a variable, repeat the test. You get a second point, pass or fail. You do this over and over again until you got a number of protection points, and you could eventually generate a protection table. And this is how every institution, every laboratory around the world did testing. And FM Global did this testing from 1960s to about 2013. In 2013, we started using a new approach, and this is the approach that we're going to be using going forward into the future. In 2013, we started to couple our modeling capabilities along with small-scale and intermediate-scale testing. This allowed us to define the problem, allowed us to define the boundaries of the situation, and then through a limited number of large-scale tests, we could verify that those boundaries of that problem were valid. And this resulted not in a single protection point, but actually in a whole suite of protection points, giving our clients many more options. And we're using this approach for multiple projects right now. To do this, you need some serious computational power. And I could talk about our modeling capabilities for an entire afternoon. So I'm just going to quickly highlight some of the complexities that it takes to develop a model of this nature. So first, you need the physics model for fire development and fire growth. You have to understand the relationship between the gas phase physics, the liquids, and the solid phase. And then, if you want to start incorporating suppression into that model, you got to determine several different things. First, you have to understand how the droplets are generated by the sprinklers. So for every sprinkler at every pressure, you have to understand what are the droplet sizes, how many droplets are being generated, what is the size, what is the trajectory, what is the velocity of those droplets. You've got to track all of that within your model. Once you know that, you got to understand how those droplets interact with the fire plume. If you have lots of small droplets with very little momentum, but you have a strong fire plume, it's going to take those droplets and either make them evaporate, or it's going to push them up along the ceiling, cooling the ceiling and potentially wetting the sprinklers adjacent to the fire origin, causing them to skip. Or you may have very large droplets that penetrate that fire plume, make it to the base of the fire, but don't cool the ceiling at all, now allowing a lot of heat of the ceiling, and now you're going to get lots of sprinkler operations. You've got to find that appropriate balance. Once you know how many droplets are being generated and how many reach the commodity surface, you have to understand how they go down the side of the material within the rack. You have to know how much of that water gets absorbed into the boxes, if the boxes can absorb water. How do they flow from one tier to the next tier? How much water is applied to the top actually makes it to the bottom of the array. Then you got to couple that with the fire dynamics model and see how the fire propagation and suppression work. And then even though the model says the answer might be this or that, you have to do testing to validate that the model is correct. So we've invested a lot of time and resources into the fire development. Now that we have this model, we can use it along with experiments to be able to look at a whole number of situations for our clients. And we did that recently. Oh, before we go to that, let me talk about what kind of computational power you need to do this. This model does not run on your standard laptop. We have a computer cluster with 1,100 compute nodes capable of 70 teraflops of scientific computing. That's 70 trillion calculations a second. If that's not enough, we actually have access to Titan, the world's second fastest supercomputer, to be able to run this model on. And I looked it up last night. Titan is capable of 18 petaflops of computing power. So that's 18 quadrillion calculations a second. That's what we're running these models on in order to be able to do this fire modeling and experimentation coupled together. So we applied this approach most recently to our INRAC program. INRACs were developed in the 1960s and 70s. The protection schemes for INRACs were developed in the 1960s and 70s. And as I mentioned earlier, we're trending towards increased storage heights and increased warehouse. So installing INRACs per the guidance from the 60s and 70s was very costly and very complex. Typically, sprinklers had to be installed at 3-meter increments at every longitudinal and transverse flue along the face as well. And you had to include sprinkler in the water calculations, the sprinklers that were in the racks and those at the ceilings. So this was very costly and you needed a very large water demand. So we decided to take a look at, could we use newer technology, larger orifice sprinklers, and replace the small orifice sprinklers and reduce the number that were needed. To do this, we used our modeling to understand where the water goes. We looked at different sprinkler layouts within the racks. We looked at how the water goes down the sides of those commodities, how much goes from tier to tier and down to the base. And then we verified that through intermediate scale testing. And it's a little hard to see in these images, but right here, there's some collection pans. So when we're running these tests, we're actually collecting the water at the base of that array, measuring how quickly it gets there and how much water actually makes it to the base. Then we couple that with some intermediate scale fire tests. If we understand in which scenarios the water was able to control that fire, we can now match it up to the different conditions that we were modeling, and we can look at different layouts that will give us that same result through the modeling and reduce the number of testing that we need. And then finally, once we have the parameter space defined, then we can do a few large-scale tests to validate those results. So for the INRAC project, we looked at our 3 standard commodities. We looked at uncartonated, unexpanded plastic. We looked at cartonated, unexpanded plastic. And we looked at uncartonated, expanded plastic. So that's like your meat trays of styrofoam, very light. And through this program, we were to develop new protection options that instead of requiring INRAC sprinklers at 3-meter increments, we can now increase that vertical separation to 9 or 12 meters, depending on the commodity. And we were able to validate these protection points with a single large-scale test for each commodity. So in the past, where we would have needed dozens of tests for each individual commodity, now we could do it with just 3 large-scale tests, saving time, resources, and money. So we were able to prove with this program that going forward, the future developing protection points is through this synergistic approach between modeling and testing. We were able to optimize the protection. We gained a fundamental understanding of the INRAC problem as well. So we're getting a lot of data and a lot of knowledge into what's going on with sprinklers as the water gets transported through the racks. And we were able to demonstrate clearly that this approach really works. So now we're applying this to 2 other scenarios. Oh, before we do that, this is what it actually looks like now. So this would have been let's imagine an 18-meter high warehouse. Previously, you would have needed INRAC sprinklers every 3 meters. With our new approach, we can eliminate a large number of those sprinklers. The ceiling only is required to protect what's above the uppermost level of in-racks. And the in-racks protect everything below that. So now you need fewer sprinklers and a lot less water. In our new designs, we're about a 6 sprinkler design for the in-racks, less than 4,000 liters per minute of water demand, and we no longer need to balance the ceiling with the in-rack sprinklers. So less water equals less money. So there's a savings for our clients in order to protect their facilities. And this protection scheme has been incorporated into Property Loss Prevention Data Sheet 8-9 and will be incorporated, hopefully, into NFPA 13 in the next revision. So because we were so successful with this approach for in-racks, we're looking at 2 other scenarios with this synergistic approach. We're looking at automatic storage and retrieval systems. As I mentioned earlier, these facilities are extremely high. They're about 37 meters as some of the ones we're seeing now in Europe. And a couple things happens when you use ASRS systems. One, you have the commodities very tightly packed. You have lots of plastic because most of the storage bins are made out of plastic, and they're open top containers. So if you start discharging water, the water doesn't make it to the base. It actually gets collected in the bins themselves. So it's very difficult to get the water to the base of the array. Makes these extremely challenging scenarios. And you also have a situation where the aisles are very narrow because they're using robotics to move the commodities up and down within the array. So you have a very tight aisle, so it's very easy to get radiant jump and fire spread from one target to the next. And each aisle has a built-in ignition source, which is the robot itself. So these are extremely challenging. So what we did is we looked at a feasibility study to understand, is there any quantity of water that can be applied through in-rack sprinklers that will control or suppress that fire? And we completed the feasibility study, and there are conditions that we can achieve success. So now we are applying that same approach that we did with our in-rack program to understand how the water gets transported through that rack using modeling, how much water gets collected in the bins, what are the optimal sprinkler designs to get that water to the base of the array. Once the water tests are completed and the model's validated, we're going to do some additional fire tests, looking at different sprinkler layouts and understanding, is the model accurate? And then hopefully we'll be able to validate this with a few large-scale tests later this year. The other scenario, roll paper. Roll paper is getting higher and higher. As I mentioned earlier, because of the overhead cranes that are now moving the paper, every configuration now is an open array. Previously, using clamp trucks, you could press the rolls of paper together, making it either a standard array or a closed array. This limited the path for fire propagation, made it a little easier to protect. With an open array, you have lots of air coming in through that arrangement. The fire grows very rapidly, and it's very difficult to control. As you can see here, first sprinkler operation occurs very rapidly. You can see here, 10 sprinklers in 7 seconds. That's if you have the right amount of water being applied. If not, if the water is insufficient, what happens is you get a rapid number of sprinklers. We had 49 sprinklers operate in 12 seconds in that test because the water was just not sufficient to control it. And 49 sprinklers operated because that's all that was installed at the ceiling. If we had more sprinklers, probably more sprinklers would have operated in that test. So we're going to use our modeling to try to understand what is the limits that can be protected with traditional ceiling level sprinklers. But there comes a point where traditional sprinklers no longer apply, and you have to look for new technologies. I'm going to talk about 2 of those right now. First, we're going to talk about smart sprinklers. Simultaneous monitoring and response technology is what SMART stands for. So as I mentioned, you have these extremely challenging fires where the fire develops very, very rapidly. So what we tried to do is come up with a prototype and a proof of concept of being able to use multiple sensors. And in our case, we used heat and smoke to be able to detect the fire very rapidly. But not only to detect it, but to also determine where it was within the array. So this sort of shows the contour plots at the ceiling. These are the temperature plots. And in our technology, what we did is we wanted to say, okay, we detected a fire, where is it? and then knowing where that fire is to open those sprinklers automatically just in that area, and to open the right amount of sprinklers to be able to control that fire and to limit the fire spread and propagation. So we did a few tests only as a proof of concept, and we were able to find that for really highly challenging fires, this works very well. It's a much faster response time to traditional sprinklers, and for the scenarios that we tested, it did result in a lower water demand and less property damage. Now the question is it going to be able to operate for those roll paper tests? Because as we mentioned, we're having activations there with traditional sprinklers to 7 to 12 seconds. So this would have to be very accurate and very rapid to be able to apply to those situations. And going forward, we'll have to see how that works. Another scenario that we're looking at, and another technology, is radiation-activated sprinklers. So in this scenario, you have sprinklers out in the open. This is a desalination plant, and you have plastic spirals on either side of these sprinklers. If a fire occurs in this structure, will these sprinklers operate? Traditional sprinklers work off convective flow. If there's no convective flow around the sprinkler, they won't operate. So what do you do to protect scenarios like that? So unless that sprinkler is embedded in that flames, it'll never operate. So what we decided to do is look at a new technology, a new way to operate sprinklers. Instead of based on the convective flow that occurs when the hot gases hit the ceiling and flow past the sprinkler, could we get a sprinkler to operate purely off radiation? And there's lots of scenarios where these could be used. Open-graded mezzanines in power plants is one scenario, where you have multiple levels that are open to each other, and there's no solid ceiling, so you're not going to get that convective flow. So we did some testing. We developed a model and a prototype, and we were able to successfully demonstrate the concept through a side-by-side test. And I know this was washed out a little bit. Sorry of the imaging and the coloring here, but here is the radiation-activated control sprinkler. Here is a traditional sprinkler. And we placed a pan right in the middle of those two sprinklers. It was a pan fire. We ignited it, and the radiation-activated controlled sprinkler operated very rapidly. The conventional sprinkler did not operate. So via this proof of concept, we were able to apply for a patent, and we patented this concept and this approach. So the intention now is, with FM Global, we have a very unique intellectual property model. We don't make or sell any fire protection products. What we're looking for is as many solutions to be in the marketplace for our clients to protect their facilities. We are an insurance company. But if we develop a new technology that is worthwhile to patent, what we will do is we will actually take that technology and we will give it away to manufacturers, license and royalty-free, for them to commercialize and make those products available on the marketplace for our clients. And that's what we're doing with this technology as well. And we're hoping someone takes it forward and commercializes it. And what we do is we provide all this information on our website, fmglobal.com/research reports. So right now, all the work for the sprinklers, sorry, I don't know why that popped up. All the work on the smart sprinklers are available on our website. There's 2 reports currently available that talk about the testing we did, the prototypes we developed, and there's a 3rd study coming out that's going to talk about the availability and reliability of smart sprinklers, and which are some of the key components that need to be monitored to make sure that that system is going to work properly when it's needed. And the work on the radiation-activated sprinkler will be posted on the website in the very near future. So the future of sprinkler technology is twofold. We need new products for where traditional sprinklers no longer are viable, and the way that we're going to develop sprinkler protection solutions is going to be through this synergistic approach between modeling and experimentation. Thank you for your time.